Yeah, Prahlad, you can go ahead.
Okay. Welcome everybody to this morning session of the STCS seminar. We are glad to have Silas Richardson from University of California, Riverside. Silas's talk was originally scheduled for the 5th of November, but like many of us, he was trumped by that date. So Silas is an expert in cryptography and security. He did his PhD from University of California, Los Angeles, his postdoc at Boston University, and is currently faculty at UC Riverside. Actually, it's curious how I got to know of Silas. I got to know of Silas thanks to one of his colleagues, Amay Bangale, who's a friend and a frequent visitor to our department, STCS. So Amay introduced me to Saurav Roy, Silas's student. So I got to work with Silas. I got to work with Saurav, and then through Saurav, got in touch with Silas, and we've sort of known each other. Silas, his original expertise was cryptography and security. He's slowly been moving on to coding theory and complexity, and he'll be talking to us on a high-dimensional Goldreich-Levin theorem. Silas, on to you.
Thank you. Yeah, it's funny that that backstory is completely correct, with the added feature that I'm not sure you're aware of, Prahlad, was I told Surya when we had this first paper, I was like, Surya, you need to use every paper, or at least when you're getting started, every paper you get, you need to use it as an excuse to like meet people in the field. You need to email like lots of people. And so I gave him a list of people he should reach out to. And Prahlad was one of them. And then Prahlad wrote back and they started working together. And I was talking to Surya and he was like, yeah, it's great. Prahlad wrote me, this is great. And I was like, oh, nice. Can you introduce me? So yeah, it was great working with you during COVID. Okay, so anyway, my name is Silas Richardson. I'm going to tell you about a high-dimensional Goldreich-Levin theorem. And yeah, this is work with Parker Newton and Chase Wilson, not from the show house. Okay, so the Goldreich-Levin theorem is an amazing theorem in theoretical computer science. Perhaps a stretch to say it's everyone's favorite theorem, but it's several people's favorite theorem, and it's a cornerstone result. It's certainly in the Hall of Fame. It's like a foundational result in cryptography, coding theory, Boolean function analysis, many more. The theorem, basically what it says is it's an algorithmic result, and it says that if you're given oracle access to a function that takes m bits of input and gives 1 bit of output, and you know that the function has good linear agreement, then the Goldreich-Levin theorem is it's an algorithm. It says it's an algorithm that allows you to efficiently recover the linear map, which has good agreement with F. Okay, and so the model here is you're given oracle access to F. That means basically you can feed it input. You can feed F inputs. You can get the outputs, but you're not trying to sort of look at the code of the function or anything. All you're doing is input-output behavior of F, and it's an algorithm that says if you have oracle access to a function with good linear agreement, you can recover the linear map that has good agreement. Okay, so here's a picture, and again, you have oracle access to this function F. You can feed it inputs, you get outputs, and when I say it has good linear agreement, what I mean is that there exists some string u, bit string, such that like the probability that the probability that f of x equals the inner product of u with x is large, and this inner product is like the vector linear algebra vector dot product, where I mean like the first bit of u times the first bit of x plus dot 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 plus the last bit of u times the last bit of x. And okay, so certainly you can imagine that if you have oracle access to a function, and if you imagine for a minute that the function has perfect linear agreement, it's just a linear map, then you can recover the linear map given oracle access. You just feed sort of the first like basis vector or the string 1 0 0 0 0 to your function, and you're going to get back the first bit of u. You do the second bit, you get back the second bit of u, and in this way you can recover every single bit of u, and so you recover the string u. And this doesn't work. This particular algorithm doesn't work as soon as you don't have perfect agreement, because if the probability that f of x agrees with u dot x is 1 minus delta, then you no longer have the guarantee that it's going to agree on like any individual input. But okay, you can do some probability. For example, you can like choose a random like basis for the vector space 0, 1 to the m. And you'll use the fact that like the the marginal of each basis vector is going to be a random string. And so, if delta is small enough, then by the union bound, you'll recover u dot x1 through u dot xm. And using this, you can like, I guess, invert the matrix or whatever and recover u. Does that make sense? Are there any questions about that? I went through that a little fast, but I mean, just shout out, I guess, if you have questions. Okay. Anyway, so okay, I'm not going to prove the full Goldreich-Levin theorem, but you can imagine that like as the probability, like the agreement probability gets further away from 1, you have to work harder and harder to recover the vector u. And what Goldreich-Levin says is that using like fancier and fancier kind of combinatorial arguments or statistical arguments, you can recover u as long as the agreement is any better than a half. Okay, so in particular, if you're given oracle access to f, such that there exists u, such that the probability that f of x equals u dot with x is at least 1/2 plus delta, then you can efficiently recover u. And this was, again, it's like an amazing result. And this is kind of, I guess, if you look up Goldreich-Levin theorem, you'll see different versions, but this is kind of the core of the law. And there's one thing I'll note that, when you let the probability of agreement get lower and lower, and in particular this low, like this close to 1/2, it might not be the case that there's a single u anymore. And okay, the Goldreich-Levin theorem says no problem. We can recover the list of all such u. In particular, the u has size polynomial in 1 over delta. And using the Goldreich-Levin theorem algorithm, you can recover every single u in this list. Namely, you can recover the set of all u that have good agreement function. Okay, and you can do it efficiently in time m and 1 over delta. Okay, so this was like a miraculous result. It came out in '89, and the original motivation for it was cryptography. And basically, if you kind of reinterpret the statement of the Goldreich-Levin theorem in cryptography language, what it says is that basically if u has cryptographic secrecy, then the bit u with x is pseudo-random. And this is like essentially a magic result that says it shows you, it gives you a method to kind of convert one-wayness into pseudo-randomness. And in cryptography, this is like a really important result because pseudo-randomness is often what you need to build like fancy cryptography gadgets like encryption and etc. And one-wayness is kind of the hardness that you often run into when you try to do algorithms, right? So like when you try to solve hard problems and you fail, that's kind of a hardness result. Or at least you have some inclination that it might be hard. But hard kind of corresponds to one-wayness, whereas pseudo-randomness is what you need. And so the Goldreich-Levin theorem is like an amazing tool to convert one-wayness into pseudo-randomness, and it's super useful. And right away, it led to a lot of different treatments of the form. One-way functions imply just tons of different types of cryptographic primitives. And it's still common today. It's just a completely standard tool in any cryptographer's tool belt. The Goldreich-Levin theorem, it comes up all the time. In Boolean function analysis, it's an algorithmic result, and essentially, if you reinterpret the statement into kind of Boolean function analysis land, it says that you can efficiently recover heavy Fourier coefficients anytime you have oracle access to a function. That's also incredibly useful. There's another kind of area of application of the Goldreich-Levin theorem to coding theory, and I want to expand on this a little bit. So the Goldreich-Levin theorem gave a decoding algorithm for the Hadamard code. And it in particular gave a list decoding algorithm for that Hadamard code. And the setting here is, in coding theory is, you have a sender who has some message, and she wants to like encode her message so that when she sends it over this noisy channel, the receiver can recover the message even if some of the bits were flipped. So kind of what I've drawn here is the sender kind of takes her message, encodes it to some string. She sends the string across the channel, and some of the bits just got accidentally flipped. Okay, so notice like the red ones are the errors, basically. That 0 was converted to a 1, that 1 was converted to a 0. And a decoding algorithm is kind of what you need in order to get this like efficient, basically in order to enable efficient communication across a noisy channel. you need to encode your message such that even if a few bits are tampered, the receiver can still kind of recover the original code word, or at least your original message from the received word. And if you sort of okay, so the Hadamard code is a particular code, and it kind of represents like a sorry, is there a question?
No.
Okay, so the Hadamard code kind of represents an extreme point on the like rate versus distance trade-off. So let me say about that. So, I mean, already you can maybe see that like there's a trade-off between how much noise is on a channel, corresponding to basically what's the probability that each bit gets flipped. There's a relationship between sort of the noise and the amount that you have to stretch your message. So like you're going to need to put, like if there's a lot of noise on the channel, namely each bit gets flipped with like pretty probability, then you're going to have to put a lot of redundancy into your code word. And so in particular, your code word is going to have to be much longer than your message. So the rate kind of measures like how much longer your code word is than your message. It's a measure of efficiency. And distance is basically how good of a job it does at making itself robust to noise on the channel. And the more noise there is, the higher the, the higher the noise, the higher the distance you need, the higher the rate you're going to have to get. And the Hadamard code is like an extremal point on this trade-off of rate versus distance. Basically, what you do is you encode your m-bit string by writing down, oh, I'm sorry, I skipped ahead. So this is just like, yeah, okay, here it is. The Hadamard code. Yeah, so you're encoding your string, m-bit string, into a 2 to the m-bit string, where every bit in the code word, sort of the bits of the code word are indexed by m-bit strings, and the bit corresponding to x, the m-bit string x, is u dot product with x. Okay, so again, you're taking your m-bit string u, and you're encoding it to a 2 to the m-bit string, indexed by m-bit strings, where the bit corresponding to x is u dot x. And okay, so you can think of like the code word as a function, takes in x and spits out u dot x. Does this make sense? Are people okay? Have people seen the Hadamard code before, or any questions here? Okay. All right, and so, but the Goldreich-Levin theorem, what it did is it said, okay, in this model, if you consider like the code, the Hadamard code, where the sender's going to take her m-bit string and she's encode it with the truth table of this function EU, where this function, it's here, it takes in x and spits out u dot x. If she sends it across this channel, then the received word is going to be it's the truth table of some function that has like pretty good agreement with EU, but it's not necessarily, equal to it because some of the bits were flipped. And the Goldreich-Levin theorem says that no problem. It says as long as the sort of function that you receive has good linear agreement, you can recover U. You can recover the original message. Okay, and important here is, I said the Hadamard code was like an extremal point in the rate distance trade-off. The rate is really bad. There's like an exponential blow up in the size. Like, if you want to encode an m-bit string, you're doing it with a truth table of size 2 to the m. And it's important that the algorithm doesn't require reading the entire truth table. So it's like a local, if you want to phrase the Goldreich-Levin theorem in terms of like this particular application to coding theory, what it says is it's a local list decoding algorithm. It's local in the sense that you don't have to read the entire input because the input is exponential size. You only have to read roughly like polynomial in m bits in order to recover U. Okay, so it's a local list decoding, local because it doesn't have to read the entire input of the entire truth table. Okay, and yeah, okay, and again, local list decoding, it just became completely standard after the Goldreich-Levin theorem was the first one, but many have followed, tons of prior work and and so on. So there's another sort of, I guess, theorem that I want to sort of say. So if you're interested in kind of local testing type, I guess, locally testable codes or just local testing in general, you probably have heard of the BLR test. The BLR test says that if you have oracle access to a function, sorry, no, it says any function that sort of has good, it passes the linearity test with good probability, must agree with some linear function. And so the linearity test that the BLR is talking about is, it works like this. It says, okay, you choose X, you choose Y, and then you feed X, Y, and X plus Y into the function, and you check whether the outputs satisfy like f of X plus f of Y equals f of X plus Y. And the BLR theorem, another super amazing theorem, it says that for any function that passes that linearity test, any function that passes that linearity test with good probability has to agree with a linear function. There has to be some linear function which like explains the test passing probability. And if you combine that with sort of the Goldreich-Levin theorem, the Goldreich-Levin theorem says that if you have oracle access to any function which passes the BLR test, you can actually recover the linear function that causes the good agreement. And okay, so this is sort of like Goldreich-Levin theorem is what you need in order to make the BLR theorem into like an algorithmic result, if that makes sense. Okay. And Goldreich-Levin has been generalized in tons of different ways over the years. You can generalize it to large modulus. In fact, like the original Goldreich-Levin theorem proof just kind of works for that setting. There's been some work generalizing it to group homomorphisms. So the setting here is you have some function between sort of general groups, and you have the guarantee that there exists some group homomorphism which has good agreement with the function, and you can sort of prove Goldreich-Levin theorems in that setting that you can like recover the group homomorphism that has good agreement. You can sort of generalize the degree of the agreement. So rather than saying that your function f has good linear agreement, you can say, okay, there's some quadratic function or cubic function that has good agreement with f. And Tolsiani and Wolff studied this for and basically they proved the degree 2 analog of the Goldreich-Levin theorem. They said basically if f has good quadratic agreement, you could recover f. And okay, so this is sort of lots of different ways to generalize Goldreich-Levin. In this work, we're going to generalize it in a different way. We're going to look at the case when the function has high dimensional output. So instead of f taking m bits and spitting out 1 bit, we're going to look at f's which take m bits and spit out n bits. And we're going to prove Goldreich-Levin type theorems in this setting. Okay. Good.
What is linear in this case?
What'd you say?
What is linear in this case? What is it?
Good. So linear, okay, let's start sort of trying to generalize this question. So here's the setup. So suppose that f takes m bits of input, gives n bits of output, and moreover, you know that there exists some matrix A such that f has good agreement with A, namely, with probability at least epsilon over the input, f of x equals A of x. Okay, the question is, all right, suppose we have oracle access to such a function f. We don't know A, but we know that there exists such an A. Can we efficiently recover A? Okay, that was sort of the question that's like one way to generalize it. And it's a pretty natural way. It's kind of like literally you just say, okay, instead of having good agreement with like a one-dimensional linear function, you have good agreement with an n-dimensional linear function. And actually,
what should I think of as n in relation to m? Should I think of n as being comparable or?
Yeah, in fact, I kind of regret the choice not to just make m and n equal to each other. So for this talk, just think of m as equal to n, and that'll, I think, make everything easier.
Okay. Okay.
Yeah.
So
you can.
Sorry, just to interrupt again. Right. So in some sense, then even if we have agreement, which is epsilon, that's a constant, that's still saying non-trivial. So for Goldreich-Levin, there was a threshold of the moment we have something bigger than half, we could hope to recover it. And here the point is any epsilon, any constant epsilon, technically speaking, one should be able to recover A. Is that
Yeah, that's a good point. I'm going to discuss this exact point that you're bringing up at length in a few slides. But yeah, basically, the threshold of Goldreich-Levin of 1/2 is kind of no longer really the right sort of threshold to think about because I mean, in the one-dimensional setting, 1/2 is a random function, right? A random function has agreement 1/2 because it's just spitting out random bits. It either agrees or doesn't. Half the time it does agree, half the time it doesn't. And Goldreich-Levin says that any better than just a random function where there's no structure at all, you can actually efficiently recover the structure. And here we're, the random threshold is quite small. The random threshold, I guess, would be like 2 to the negative n. And so, like, if we really wanted to capture what I feel is like the spirit of the Goldreich-Levin theorem, we should be saying any bigger than 2 to the negative n. As long as the agreement is any bigger than 2 to the negative n, let's try to recover the structure. And we don't actually get quite that good, but we get something that's like similar to that. Does that make sense?
Yes, that makes sense. Yeah, thanks.
Yeah. Silas, since you mentioned BLR also, there's also the corresponding testing question in this world. And that's this related to the polynomial Freeman-Ruscha. And will you be talking about that also?
I have a slide on that. And sorry, I didn't. What was your question?
No, my question was, how is this? So you're asking about the recovery, the decoding question. There's also the testing question, given that you mentioned BLR. And here, this is the polynomial, well, it's related to the Freeman-Ruscha theorem and the polynomial Freeman-Ruscha conjecture.
Right. Yeah. So so the testing question is like the high dimensional version of BLR is actually kind of equivalent to the polynomial Freeman-Ruscha conjecture, which is now like a theorem. And so it's now known that if any function has good linear agreement, if any function passes the BLR test with good probability, then there must exist some linear map that is sort of explaining the test passing success. And then what we're saying is you can recover that linear map. And I'll talk a little bit about, so we're not using techniques from additive combinatorics at all. And I'm going to talk a little bit about some, basically a couple of different things on that topic. One is sort of like, can you use techniques from additive combinatorics to just like solve this? And the answer is, I'm not sure. On Terry Tao's blog, I believe, he had some, or maybe in like one of the papers, they have some statement where they say like, yeah, these techniques are all algorithmic, and so you can get some algorithm. And so that would sort of suggest that if you have oracle access to some function that passes the BLR test, you could recover using like a proof, a matrix. However, I'm not sure. I haven't like checked that, and I think there's a lot of stuff that needs to be checked for that. Number two is the parameters that you're going to get aren't quite good. There's going to be a loss, and in particular, you'll recover, assuming that you can, in fact, like algorithmatize or whatever their result, you'll recover a matrix that has agreement like epsilon to the 10 or epsilon to the 100 or something, some polynomial in epsilon, and we're going to sort of do better, I guess. So, okay. Explicitly, like, here's one way to sort of try to recover a matrix. You say, okay, F has good agreement, therefore it's going to pass some BLR test with good probability. That's true. Therefore, you can try to just like use the Freeman-Ruscha theorem to try to recover A. If you do that, you're going to get an A that has much worse agreement than this A, that like much worse agreement than epsilon. Does that make sense?
Mm-hmm.
Anyway, I'll have slides on that too in a bit, so we can like look a little more carefully. But anyway, okay, so again, the setup is have some function, m bits of input, n bits of output, and it agrees with some matrix A with probability epsilon. We efficiently recover A. And the answer is, okay, it depends on epsilon. If epsilon is 2 to the negative n, then no. Because this is like the random parameter, the probability, sorry. F is a random function. It's going to have agreement 2 to the negative n. So you're not there's no structure in such a random F. So certainly the answer is no, you can't recover anything if epsilon is just 2 to the negative n. If epsilon is bigger than 1/2, if we're in the like 1/2 plus delta regime, then the answer is yes. And really, this is kind of the original Goldreich-Levin theorem, lets you just recover kind of each row of A. And you have to do a little bit of work, but this is sort of prior work takes care of this. So the question is like, what about in between 2 to the negative n and 1/2? And the sort of sad answer is no, actually. If epsilon is less than 1/2, then no, there's no hope of recovering A for the following reason. Essentially, the answer is we kind of asked the wrong question. We're going to have to like modify the question we're asking. And let me show you why. Okay, so here's kind of a counterexample, and this is kind of actually a problematic function for a lot of different stages of our algorithm. So we're going to keep coming back to this. But okay, here's a function. Fix some A, some matrix A, and define the function f as follows. The first bit is simply random, and the last n-1 bits, so basically bit 2, 3, 4, all the way to n, is just ax, the ith bit of ax. So if you want to think of this as like the ith row of A interproducted with x. Okay, so the first bit is random, and all the rest of the bits are correct. And okay, the probability that f of x equals ax is a half, certainly. We all agree. But notice that probability that f of x equals a prime of x is going to equal half for any matrix a prime that shares same second through nth rows with A. So basically what I'm saying is you can get a whole family of matrices that agree with probability of half by taking the second through nth rows of A and then just making the first row whatever you want. And that makes sense, right? There's no information inside F about the first row of A. It's simply outputting a random bit. And so this is like an exponential size family of matrices. So you can't, there's no hope of like recovering A, per se, because A is just like simply one member of this exponential size family. Right. So since sort of the family of matrices that has good agreement, with this function f has size 2 to them, we can't hope to recover A efficiently. But sort of we asked the wrong question. So this is like an unsatisfying answer, because there's a huge gap. I mean, first of all, it's sad, right? It would be sad if this were like the end of the story, because there's a big gap between 2 to the negative n, which is like the random agreement threshold, and 1/2 plus delta, where the original Goldreich-Levin theorem works. So, we would hope that we can say something in this range, and we can. And so the question is anything possible? And the answer is yes. And the key point, sort of that kind of saves us from counterexamples like this, is that the exponential family of matrices that you get from this counterexample, they all agree with it for the same reason. There's no like it's not like you could recover one matrix from this family and then recover another matrix from this family and like gain any information, right? They would still have the same second through nth rows. And so the goal shouldn't be to recover the entire family, because that's repetitive. It's like the information you've already recovered simply by recovering one of these things. And so so to answer this question, what about, when this agreement is between 2 to the negative n and 1/2? Well, okay, you can't recover A, but you can recover, what we show is you can recover some A prime, which is like morally just as good. In this case, sort of in the case of the counterexample, you would recover some matrix that has the correct second through nth rows, and you would like the first row would be whatever, but there's no information in there anyway. And so, okay. So the way that this is sometimes phrased is you can't recover A, but you can recover A prime that kind of explains all of the agreement that A explains. So the sort of explanatory value of A prime and A is the same. Sorry, does that make sense?
That makes sense, but is it clear that the number of different A's which are corresponding to these different families, you'll be defining different, are still polynomial sized, or?
The number of different families you're asking?
Yes.
Yeah, so that's okay. So here's our theorem, and I'm going to sort of say it, and then we can walk through it. So, okay, the efficient algorithm, given oracle access to F, which outputs a set of matrices of polynomial size, or epsilon to the negative 1 over epsilon, such that every matrix in your list has agreement roughly epsilon with F. And moreover, for any other matrix that has agreement epsilon with F, there exists some matrix in your list that has good epsilon squared agreement with A prime. So, okay, to say number 2 again, any matrix that has good agreement with F agrees with something in your list. Okay, so you can recover a short list which explains all of the linear agreement in the sense that any matrix which has good agreement with F has good agreement with something in your list. Okay, this is sometimes called approximate list decoding. It's basically, it's sort of so okay, list decoding is an attempt to decode even when you sort of have too many errors to do unique decoding. And so you say, okay, let's give up on recovering a single code word. Let's recover the entire list of code words that has good agreement with whatever, with our corrupted code word. And there are kind of as you decrease the agreement, you eventually will lose the guarantee that the list of code words that have good agreement is polynomial sized. But you can still try to ask decoding type questions, and approximate list decoding is kind of a method to do list decoding even in settings where the list is exponentially large. And so you say, okay, we're not going to try to recover the whole list. That would take exponential time. Instead, let's try to like recover a short list that explains all of the matrices that has good agreement.
Silas, question here. So can you actually strengthen the final item 2 to state that for every a prime such that f of x equals a prime x is at least epsilon, you can find another a such that the set of agreements of f with a and f with a prime are the same as what you had for the example? Or is that too good to ask?
I am not sure that you can do that. I'm also not sure that it's too much to ask. I do know that you can put f in here, like sort of I took it out just to make it simpler, but the actual event inside this probability is actually that a prime of x equals f of x equals a of x. So like a prime and a share like a lot of the common like the basically each of the matrix agreements with f overlaps quite a bit. I'm not sure that it's going to be possible to say that it's equal.
Okay.
You know, so there are kind of two counterexamples to keep in mind. This is this is sort of intuitive. It's not like it's this isn't like a rigorous statement or something, but sort of from my experience working with this question, two kind of useful counterexamples that are like on opposite ends of the spectrum are the one I showed where it's doing the correct thing except for one sort of bit, which it's flipping randomly. And the sort of more standard like problematic decoding thing where it's like alternating between a few, like it's alternating its agreement between a few different matrices. So what I mean by that is like, let's say there are two matrices A1 and A2, and your function f is just like splitting the input set in half. Half the time it's agreeing with A1, half the time it's agreeing with A2.
Okay.
And my feeling is you might be able to combine, like you have to deal with sort of combinations of the two counterexamples, and that might kind of throw off what you're trying to say.
Okay.
I'm not, but anyway, it's a good question. Okay, there's one thing I want to say. This is like a theorem, right? Very good, but there are some problems. In particular, I will show you the algorithm to do this, but I don't believe it's the correct algorithm. In particular, it's not efficient. It's not polynomial time. It's sort of quasi-polynomial. Like the exponents are these like logarithmic factors of 1 over epsilon. So in particular, it runs in time m to the log of 1 over epsilon and epsilon to the negative log of 1 over epsilon. And really what we'd want is it's like polynomial in m and 1 over epsilon. That would be like a real nice theorem. And what this says to me is that we don't quite have the right algorithm. And so I'll talk about that. But anyway, so the algorithm I'm going to show you, it does, you know, it's efficient in some parameter regimes, in particular if this, you know, exponent is like constant or whatever. Anyway, so yeah, one could hope that we could do better, I guess is what I'm saying. So this is like an interesting question, whether you can get a polynomial time in m, polynomial in 1 over epsilon algorithm to solve this problem.
Okay.
Yeah.
So right now you're asking whether the agreement is an epsilon fraction. Ideally, I would have liked to have, what can we say when you have advantage over random? 1 over 2 to the n plus epsilon. And I would like to characterize it in terms of that epsilon, the advantage rather than this. But almost all results in this area, even the PFR are all stated in this. Is there a reason? Is that we don't know how to get to such sharp results? Or is there a reason for this? Or
it's a good question. I don't know I don't, one of the things I like about this result is that you don't have to get into the additive combinatorics. I do believe that you could hope for something for a statement in this context of the form like, it has agreement 2 to the n plus epsilon, and then you could try to get something in terms of epsilon.
Okay.
We weren't able to for kind of some annoying reasons, but I think we also didn't work extremely hard to push this all the way down. Because anyway, it kind of felt like we had the wrong algorithm. And so I think there's no reason, in my opinion, this algorithm shouldn't have a 2 to the negative n plus delta here.
Okay.
Yeah. Okay. So yeah, this is just kind of what I said. Intuitively, like, in some sense, this is kind of the best you could hope for because the set of matrices with agreement epsilon could be exponentially large. And so what we're saying is we're not recovering the whole set. We're recovering a short set, a sort of polynomially bounded set that explains all of the agreement. Okay.
Pranab, I asked about your question. You write it as 1 over 2 to the n plus epsilon. What is roughly the epsilon you're looking at?
No, so hoping that GL epsilon will be something, anything better, any advantage over epsilon, I want to get something. No, basically I was wondering if the GL theorem is a consequence of this. But because the GL theorem, the list has to have because this has a slightly smaller size list than the GL theorem. It has a 1 over epsilon size list than a 1 over epsilon square size list, which the GL. So I was wondering if such a statement would be true for GL, whereas GL, you can't expect such a thing because any two things in the output are very, very far away from each other. Condition 2 won't be satisfied at all. So
what I was getting at,
in terms of advantage, things will 1 and 2 will have to be restated slightly.
What I was getting at is if epsilon is, let's say, at least an exponential, it's at least 2 to the minus n, then it's off only by a constant factor.
Yeah. So it's off only by a constant factor. But I would like to say any deviation, that is, it could be off by epsilon by 1 over 2 to the n square, and I want to know still do you get is there a reason for it, or is random the worst example, or are there other examples out there?
Oh, so
because BLR tells you Goldreich-Levin tells you random is the worst example. BLR and Goldreich are saying random is the worst. It's unclear what's happening over here.
Yeah. Okay. I'll come back to this. Okay, no, this is short. I'll say it now. So, okay, so just like Goldreich-Levin gave a list decoding algorithm for the Hadamard code, this gives a list decoding algorithm for the high-dimensional Hadamard code, which isn't really a real thing. But you can kind of generalize the Hadamard code to higher dimensions the natural way. You say, okay, we're going to encode a matrix by like the truth table of matrix multiplication. And, okay, our result is going to give an approximate list decoding algorithm for this code. The high-dimensional Hadamard code, so one thing that's kind of funny about it, it's a bad code in the sense that it doesn't have any, like the distance is still a half, right? Everyone knows, like the distance of Hadamard, the one-dimensional thing is 1/2. And you're not gaining any factor of improvement in the distance by making it high-dimensional. And so for that reason, I mean, this isn't a real code sort of because of that. Like, it's not going to give you any better distance, so like, why bother doing it? But if you relax sort of, it's still going to have a good decoding. It's an approximate list decoding, right? So in order to sort of like the parameter regime where you can hope to get some kind of different behavior between the high-dimensional Hadamard code and the basic Hadamard code is when you have agreement much less than 1/2. And already when you go down below 1/2, you're below the minimum distance, and so you're not going to have like nice list sizes or anything like that. And so, but okay, so now you have to deal with like approximate list decoding, not regular list decoding. And I think that it might be that the high-dimensional Hadamard code does have applications. I mean, the Hadamard code has tons of applications, and it might be that some of them will kind of like generalize up to high dimensions, it's just a little bit harder to work with because it doesn't give you any better distance. And so, you know, a lot of the theorems that you might hope are true are not quite true. You have to kind of do like approximate list decoding versions of the stuff. And so anyway, that's just a feeling.
By the way, you should be writing the alphabet of this high dimensional alpha is actually 0, 1 to the power n, no? It's not the Boolean alphabet.
Yeah. Correct. Yeah. So good point. There should be like a 0, 1 to the n parentheses to the 2 to the m.
Yeah. Okay.
Yeah, that's right. Okay, this is kind of more like what we were talking about. So there's this high dimensional version of the BLR test, which is like known to be equivalent to some versions of this polynomial Freeman-Ruzha conjecture, which was recently like proved. So it's a theorem now, and that was very exciting. That's a sort of very difficult and it's like a very difficult and deep result in additive combinatorics, which is like a branch of math, but it has tons of applications in computer science. One of which is it gives you an analysis of the high dimensional BLR test. And so, okay, what's the high dimensional BLR test? Well, it says if you know any function that passes the linearity test, f of x plus y equals f of x plus f of y, with probability at least epsilon, there has to exist some matrix A that has good linear agreement. Okay, so our result fits kind of downstream of this, says that like, okay, we can actually, you know, if any f that passes the BLR test, we can actually efficiently recover the matrix A. But okay, back to just the BLR test. So this was first sort of analyzed by Semmeroditsky in 2007, where he kind of connected it to additive combinatorics. This was like a great paper. And then improvements to the additive combinatorics, there was like a breakthrough of Sanders in 2012, and then recently, you know, they actually proved the theorem. You know, they've given basically better and better relationships between epsilon prime and epsilon. Okay, so the BLR test is saying that if you have the test passing probability of epsilon, then you have agreement epsilon prime, where originally epsilon prime was like exponential, and then recently it was proven to be polynomial. So, you know, epsilon to the 10 or something like that. And our result fits downstream of this. That's one thing. But the other thing that I wanted to say is this is like on the topic of like, can't you just use the techniques of this proof to like do what we're trying to do? And I don't know. That's probably like you can probably use them to do some version that's not going to be quite as good. But I think a really more interesting question is like, can you use our techniques to look at? So forget the additive combinatorics statement of the polynomial Freeman-Ruzha theorem. Let's just look at high dimensional BLR. It's known to be equivalent. So let's just try to prove high dimensional BLR. Is there a version of a proof of high dimensional BLR which doesn't sort of just use the advances in additive combinatorics? Instead, can you do it using the techniques that I'm about to show you? And the answer, I'm not sure. I think that, you know, you can sort of hope that maybe there's something there. And I think it's a really interesting question. And I'll just say that, like, you know, it might be that sort of like, okay, the equivalence between high dimensional BLR and the normal statement of polynomial Freeman-Ruzha already includes some kind of hardcore additive combinatorics. You need Balog-Summary-Gowers, you need sort of Ruzha calculus, other techniques like this, simply to show that like a proof of high dimensional BLR gives you the polynomial Freeman-Ruzha theorem. So it's possible that like it's possible that basically high dimensional BLR is just simply easier to prove than the polynomial Freeman-Ruzha theorem. And it might be sort of that like, you know, you can get like a more basic proof of high dimensional BLR and use those techniques downstream to give you like another easier or more, at least more computer science friendly proof of this like important PFR theorem. I think that's a cool direction. And anyway, I haven't worked on it. I'm sort of more interested or more curious about making an actual efficient algorithm, but this is definitely something I think is cool. Or at least an interesting question. Okay. Anyway, so I'm going to now talk about the algorithm and the analysis. Are we out of time? We are, right?
15 minutes.
15? Okay, that's plenty. Okay, great. So, so here's what we're going to do. So remember, we're sort of given oracle access to this function f. Namely, we can feed it inputs and we get outputs. And we know that there exists some matrix A that has good, you know, that agrees with this function f with probability epsilon. And our goal is to recover some A prime, which is like morally just as good as A. That's our goal. Instead of that, we're going to focus on kind of an easier goal to understand, which is just, I want to know whether the output I received is equal to A of X. This is like the question that I care about. I want to build a way so that I can give an input X, and then what I tell when I receive an output, whether it's actually equal to A of X or not. Okay, and if you can answer this question, then you can just recover A, just by kind of like feeding a basis X and choosing to keep the responses that are correct, and then you can kind of like recover AXI or basis, X1 through XM, and then you can like recover this matrix A. Okay, so again, we're not gonna like worry about that. We're simply gonna worry about this question. Can we tell, is there a way that we can tell if f of X equals, if the output that we're getting is equal to A of X or not? So at the beginning of the algorithm, you have no kind of information other than you know that it agrees with probability epsilon, but you don't know how to, you don't know any more than that. So you receive an output, you're like, okay, well, with probability epsilon, it's good, but I don't know anything. I can't tell. But what we're going to do is we're going to basically build a way to kind of make a few guesses. And if our guesses were lucky, then we're going to kind of condition on those guesses. And then we're going to have a better idea of how to answer this question. That's kind of what we're getting ready to do. All right. So here's a question. Can we recover the first row of A? Forget recovering the whole matrix. Can we recover the first row? Maybe, that's the type of thing you could just use the one-dimensional Goldreich-Levin theorem for. And okay, well, if we had a guarantee that like f of X agreed with the first row with probably 1/2 delta, then you could use one-dimensional Goldreich-Levin. The problem is this guarantee, it only gives us a probability epsilon of agreeing with the first row. It doesn't give us this like nice 1/2 plus delta that you need for one-dimensional Goldreich-Levin. However, if you instead of looking at like the first row, if you look at just a random row, or even more generally like a random linear combinations of the rows of A, then that is going to be in this sort of 1/2 plus delta regime. So the kind of key computation for that is, let's look at this sort of probability that Z inner product with f of X equals Z inner product with AX, and let's look at it in like expectation over a random Z. Okay, you can kind of compute this probability, and you're going to get that it's 1/2 plus epsilon over 2, where epsilon is this like linear agreement. Okay, there are a couple ways to do this calculation. You can kind of just do it, or you can understand that like, in the epsilon, in the cases when f of X equals A of X, you're going to have this agreement holding. And in the cases when f of X is not equal to A of X, you're going to have this agreement holding with probability 1/2. And if you put those together, you're going to get that sort of the expected value of the agreement of Z inner product f of X with Z inner product AX is 1/2 plus epsilon over 2. Okay, and what that means, it gives us this like procedure, this kind of, starting point where, okay, we want to choose some random Z. We think of this as choosing like a random linear combinations of the rows of A. And we want to run one-dimensional Goldreich-Levin theorem on the function f sub Z, which is basically Z inner product with f of X. Okay, if we got lucky with our choice of Z, then this is going to have agreement 1/2 plus epsilon over 2, or actually 1/2 plus epsilon over 4. But yeah, so this is kind of the key thing. With probability like roughly epsilon over Z, we're going to have picked a good Z. Namely, this function f sub Z is going to have agreement 1/2 plus roughly epsilon with X. This function f sub Z is going to have agreement roughly 1/2 plus epsilon with Z inner product with AX, namely A transpose Z inner product with X. Does this make sense? Sort of what we're saying is, what we're saying is basically we're choosing a random Z. We think of this as like a random, row vector, and we're looking at the function. We're looking at the one-dimensional function, which takes X and spits out Z inner product with f of X. And if we got lucky, then this function fz is going to have good agreement with A transpose Z dotted with X. Okay, I'm using the fact that Z inner product with A of X is the same as A transpose Z inner product with X. Okay, and so if we got lucky with our choice of Z, and we got lucky with our like application of the one-dimensional Goldreich-Levin theorem, we're going to recover this vector A transpose times Z, which you can think about as being basically one row of the matrix A. Okay, so we have this random procedure. It chooses a random Z. It runs the Goldreich-Levin theorem. It hopes everything got lucky. And what you can show is that like with probability roughly epsilon cubed, you will have gotten lucky. So you will have recovered Z and then the A transpose times Z, which you can think of as like one row of A.
So Silas, at this point,
Yeah.
we will still have a list, right? A list of candidates that could be the
Yeah, exactly. So if you got lucky with your choice of Z, then you will have a whole list of vectors that can agree with Z. And basically what I'm saying is just pick one of them. Hope you got lucky.
I see. Okay.
Hope you got lucky in the list too.
Okay.
Okay, so this epsilon cubed is exactly like the probability that epsilon that Z is good, and then the probability epsilon squared that you picked the correct thing.
Okay, got it. Yeah.
Okay, but this is like important. I mean, okay, so first of all, yeah, so this is like the summary of that several slides. Like we have this procedure that with probability epsilon cubed can recover a single row of the matrix A. It's a Z comma A transpose times Z. And this is not the type of thing that you're going to want to recover. You're going to like want to use to recover every single row, because that's going to have an exponential probability of success. It's going to decay exponentially. But if you just go back to this question, I wonder if f of x equals a of x. Well, if you run the procedure one time, you recover one row of A. Now you have like a hint as to whether the output that you're receiving is actually equal to A times X. Namely, you inner product the output you got with Z, and you look at whether it's equal to this thing inner product with X. Okay, so, right, like now if you get an output, let's say you've recovered one row of A. If you get an output f of x, you no longer have to wonder whether f equals a of x. You only have to wonder whether it's equal, given that it agrees with the like one linear combination that you've covered. Does that make sense?
Yeah.
Okay, so what this sort of suggests a let me skip ahead to the picture. I'll come back and tell you about what I skipped. But this basically suggests a procedure. This is like kind of a greedy algorithm, a very simple greedy algorithm that's going to use that procedure. So you initialize some set S to be the entire input space. And this blue set is kind of the X's that you're hunting for. These are the X's where the function agrees with your matrix. Okay? And what you're going to do is you're going to run this procedure one time. You're going to recover one row of the matrix A. And you're going to then shrink S to kind of throw away all of the inputs that don't agree with that row. Okay, then you run the procedure again. You're going to shrink S again to throw away all the inputs that don't agree with the second row that you found. You're going to run this procedure like a few times, and you hope that after you run it a small number of times, you've shrunk the set so much that it's like basically just equal to this blue set. And now you can kind of, right, and the point is that like the yellow set is testable. You can check. The yellow set is simply like the set of inputs which agree with the linear combinations you've extracted already. And so the hope is if you can sort of shrink the yellow set so it's close enough to the blue set, then you can answer this question, right? You can answer the question of does f of x equal a of x, because you have this like efficiently testable like proxy for whether the input is in the blue set, right? You hope to achieve that like the probability that you're in the blue set, given that you're in the yellow set, is like close to 1. And that's going to be kind of the algorithm that we try. Okay, so let me go back and kind of explain this a little bit. Here's like the pseudocode of this greedy algorithm. Again, so let me go back to here. So we have this procedure that can recover a single row of A with probability epsilon cubed. So that's going to allow us to hopefully convert this question of does f of x equal a of x into like an easier question, which is does f of x equal a of x, given that this output agrees with all of the linear combinations that we've extracted already. Okay, and so the hope is that basically the probability that f of x equals a of x, given that you have agreement with all the stuff you've extracted, we hope that this probability is like significantly bigger than epsilon. We hope that we've sort of made this probability bigger by just conditioning on this one row. And okay, so this is going to sort of suggest the following greedy algorithm. You initialize a set S to everything. And the main loop is just you're going to run it t times, where t is some parameter we'll pick later, where you run the procedure, you recover one row of A, and then you update your set to basically throw away all of the inputs that don't agree with the linear combination you've picked, you've extracted, you've recovered. Okay, so namely, you keep the X's in the set that agree with the linear combination you've recovered, and then you just do this t times, and eventually you output the set S, and then we're going to use membership in S as like a proxy for whether or not f of x equals a of x. Okay, and if you bring to this picture that what the algorithm's doing is S is initialized to everything, then you run the procedure once, you shrink S, twice you shrink S, you keep going, and you hope that after running it a small number of times, you've shrunk it so much that it's going to basically be roughly equal to the blue set. Namely, the probability that you're in the blue set, given that you're in the yellow set, is roughly 1. Okay, and if we can get that, then we can use membership in S as like a proxy for f of x equaling a of x. Okay, this turns out not to work. You can analyze this, and I'm not going to do it because I'm kind of out of time. But basically, I want to show you basically that algorithm run on 2 examples. This one is the example that that we talked about at the beginning, where like the first bit is random and the rest of it is the same. Like the rest of the output is correct. And example 2 is basically this like alternating function where half of the inputs agree with A and the other half agree with A prime. And I want to sort of, the takeaway is basically the algorithm, the greedy algorithm I said is going to run well on example 2. It's going to work. On example 1, it's not going to work. And so we need to kind of, excuse me, I would say kind of the main contribution of this work is kind of understanding and categorizing like what types of conditions have to be in play in order to make the algorithm that I just wrote down fail. And we kind of like collected we basically understood like what can go wrong, and then we have a way to like make progress in that case. So the final algorithm is going to kind of be like a branching 2 different things. Like either conditions are going to be such that that greedy algorithm makes progress, or they're not, in which case we can like make progress in this other way. Okay, and these 2 examples are going to show you like how to make progress. Example 2 is just the greedy algorithm that I just wrote is going to work, and then I'll tell you about how to make progress in the example 1 case. Okay, so let me I guess go back now and tell you about just a little bit about the analysis, not because just so that you can understand kind of the two example functions. So I kind of said this already, but like in this algorithm, the key sort of one way to think about what this algorithm is doing is you run this procedure, you recover a row of A, and then you like update the function to basically like the function kind of like throws away all of the inputs where this linear condition doesn't hold. And you look at like what happens to this new function, how often this new function agrees with that, with the matrix A. So basically when you update the function to kind of, let's say, output a random output when this linear condition doesn't hold, and then you study like how good agreement does that new function have with A? The new function is going to have this agreement, probability that f of x equals a of x, given that z dot f of x equals z dot a of x. And the hope is that this probability is like much bigger than this probability. Okay, you can show that this probability is just epsilon over the probability that your linear condition holds. And so really what you want is that you want this linear condition to hold with probability that's bounded away from 1. Okay, so you want, it's kind of this weird like 2-sided condition that you need. So you choose a random z, and you need the probability that you agree with, like the linear condition, to be bigger than 1/2 in order to like run the Goldreich-Levin theorem, have it succeed, and then add the linear condition to your set. But you also need it to be bounded away from 1 so that the probability like updates in a positive way. In particular, you want to move from like epsilon to like a constant multiplicative factor bigger than epsilon. So really, you need this quantity. Q of z is like the probability over x that z inner product f of x equals z x, given that you're in S. Basically, it's the probability that this linear condition holds. You need this probability here to be between 1/2 plus epsilon and 0.99. The upper bound is so that you can make progress, so that like essentially so that the yellow set is shrinking, and the bigger than 1/2 is so that you can recover the Goldreich-Levin like the linear condition via the Goldreich-Levin algorithm.
Sorry. So which means that in the other example that you had, where just the first coordinate was off, is it that the probability is not bounded away from 1? Is that what happens?
Correct.
Correct. Okay.
Right. And so basically what happens is if you run this picture thing, you're going to like recover a linear condition. The S isn't going to shrink. And so it's just going to stay the same. You're not going to make any progress. That's kind of the thing we can. And okay, so to analyze like what happens to the algorithm for these two functions, let's start with the one works. Let's start with this sort of example 2. So at the beginning, the probability that you agree with A is 1/2, because half the time you're here, half the time you're here. And that means basically that the probability that like, over z or whatever, the probability that you agree with the linear condition, basically the probability that z inner product f of x equals z dot a of x is going to be 3/4, because it's going to be like, it's going to agree with probability 1 when you're in this case, and it's going to agree with probability 1/2 when you're in this case. So you're going to get like 1/2 plus 1/4, basically. And so you're going to get 3/4. And what that means, that's bounded away from 1. That's good. So that means that basically when you choose a random, when you choose a random like z, you run Goldreich-Levin, you recover some like linear condition, you're going to make progress. The new p is going to be bigger than 1/2. It's going to be, you can compute, it's going to be 2/3. You do this again, you're going to 5, 6, and this is a little misleading. It's like the pattern here, this is going to get like exponentially close to 1. You do this like k times, you're going to get to basically 1 minus 2 to the negative k. And so this sort of indicates that the yellow set is like decreasing at a really fast rate and it'll become roughly equal to the blue set pretty quickly, and that's good. And this just has to do with like you compute this Q, and again, I only computed it one time, but each time it's going to be roughly the same computation. It's going to be the probability that you're in the right partition times 1 plus the probability that you're in the wrong partition times 1/2. That's kind of the idea. And okay. In this example, you have kind of this awkward situation where you start with probability just equal to 1/2, because it's equal, whether or not f equals a of x is just whether or not the first bit is correct. Okay, and if you look at these Qs, the probability that this linear agreement holds is going to either be 1 if the first bit of z is 0. That would kind of kill this like random bit, right? If you multiply f of x by z and the first bit of z is 0, it's going to kill this row. It's going to kill this coordinate of f. And so it's going to kill the random coordinate. And so you're just going to always agree with like z inner product ax. On the other hand, if z1 is 1, then you keep this random bit. And so you're agreeing with probability 1/2. And so this is bad. This means that every z is either going to be so small that you're not even going to be able to run the Goldreich-Levin theorem. It's simply a random function. Or it's going to be so high that you're not going to shrink your yellow set at all. Okay, so yeah, basically, if you pick a z that has first bit 0, you're not going to make any progress in this sort of quantity p. Like the agreement with your a of x conditioned on agreeing with the linear condition you've extracted isn't going to go down. Or it's going to increase, I mean. Okay, so let me sort of go through this quickly. The Goldreich-Levin progress condition. Let me skip ahead a little bit. So basically, there are kind of two cases. Case one is like when things are not working, the greedy algorithm does not work, and case 2 is where it does work. And we sort of define the Goldreich-Levin progress condition to be like whether, the Goldreich progress condition, if it holds, you're going to be able to make progress through that basic greedy algorithm. This is sort of kind of you're in example 2. The problem is you're not always in example 2. You could be in example 1. And so the key of our kind of work, I would say, is figuring out how to make progress when the Goldreich-Levin progress condition doesn't hold. And the answer, I'll sort of just skip ahead to what it looks like in the picture. The answer is basically to reimagine what it means to be equal to A of x. I want to say, no, I don't care about actually equaling A of x. I'm going to say, I only care about being equal to A of x plus something in a small dimensional vector space. Okay, so you initialize 2 things now. You initialize W to the 0 space and S to be everything. And then you make progress in one of 2 ways. Either the Goldreich-Levin progress condition holds, in which case, great, you do the Z thing, you choose a random row, and then you shrink the yellow set. And this is going to allow you to make progress whenever the Goldreich-Levin condition holds. Or the Goldreich-Levin progress condition does not hold, in which case you say, no, I don't care about actually being equal to A of x. I don't actually want F to look at the blue set where it's equal to A of x. I want to expand the blue set. I basically want to relax what I mean by being equal to A of x. And I want to say that I'm going to count equality as being sort of equal to A of x plus something in a small dimensional subspace. And so I'm basically increasing the blue set when the Goldreich-Levin progress condition doesn't hold. And when it does hold, you shrink, and it does not hold, you increase blue. And you're going to get them to be equal in kind of like, a few number of steps. Because either the Goldreich-Levin progress condition holds, so you can make progress by shrinking the yellow set, or it doesn't hold, in which case you can make progress by increasing the blue set. And I just want to say that if you look at this example where it doesn't hold, this is the same example. Like the first bit is random, other bits are correct. The probability that you equal A of x is 1/2, as we know, but the probability that you're in A of x plus the span of the first coordinate is just 1. You're always like equal to A of x. You're either equal to A of x or you're equal to A of x plus the first unit vector. And so what we sort of figured out is that like when the Goldreich-Levin progress condition does not hold, when you're not likely to make progress by like choosing a random linear condition and conditioning on it, then it has to be that there's some subspace that you can sort of add to what we mean by being equal to A of x, and you can greatly increase this probability. So this probability either increases by conditioning on agreeing with some linear condition, or you can increase it by relaxing what you mean by being equal. And you say, no, I don't care about being equal. I want to include things that are in this, like that are equal to plus something in a small dimensional subspace, and then you make a lot of progress there. And the way you prove it is Fourier analysis. I won't talk about it. But anyway, okay, so that's kind of the end. So the last picture one more time, the way the algorithm looks is you initialize S to be everything, W to be 0, and then when the Goldreich-Levin progress condition holds, you choose a random Z, you do the one-dimensional Goldreich-Levin thing, and you make progress by shrinking S. When it doesn't hold, you relax what you mean by being equal, and you sort of expand the blue thing. Okay, and I think that's it.
Questions?
Any questions? Sorry, I went a couple minutes over.
What's the significance of epsilon square in the second condition?
Say that again, I couldn't hear, sorry.
In the theorem, there's an epsilon square in the second condition. Is that, did you try to improve it? Is that natural? How should I understand it?
Sorry, where's the epsilon squared?
So you promise that any matrix that agrees with A also agrees with,
Yeah, I gotcha. I'm going back to it. Sorry. Okay, here. You're talking about this?
yeah.
Yeah, it's a good question. Honestly, I'm not sure. We never looked into improving this. I sort of, the way we prove the theorem is we show that you can recover a single A, and then you kind of, given that you recovered the single A, you like update the function to disagree with the A that you've recovered, and then you just iterate, and you'll wind up recovering a list. And what you show is that the probability of agreement is epsilon squared. And I sort of didn't try to improve this because I thought this was normal. At least in like, sorry. My only point of comparison were these like polynomial codes where I see this parameter popping up a lot. I think it has to do with like the Johnson bound. And but you're right, in the original Goldreich-Levin theorem, it's not. it's epsilon here and then epsilon to the -2 here. So
Yeah.
we didn't like understanding the trade-off and the different options. That's a good question.
Okay. Any other questions? Okay, thanks Silas again. Can you, Ramprasad, can you turn off the stream?